This lecture is about sound. So at this point of the unit, we're going to focus a little bit more on sound waves rather than waves in general. From our earliest years, we become accustomed to a great variety of sounds. Sound is a form of energy we can hear. Some of these sounds are pleasant to the ear and some are not. They are called sounds because they stimulate the auditory nerve in the human ear. So a sound is a form of energy we can hear. Just like all waves, they're produced by a vibrating object. We have different categories of sound waves, and for humans, we can define audible and inaudible sound waves. The range of human hearing is about 20 hertz on the low end to 20,000 hertz on the high end. Those are frequencies, of course. And anything that is below 20 hertz is called infrasonic, and anything above 20,000 is called ultrasonic. So here we are, category of sound waves, audible and the inaudible, which are infrasonic and ultrasonic, which are, of course are broken up into below 20 hertz and greater than 20 kilohertz. Noise pollution from industrial, transportation, entertainment, and other sources can increase stress, lead to hearing loss, disrupt ecosystems, and alter animal behavior. Noise pollution can be reduced by using mufflers, sound barriers, baffles, and earplugs, and by turning down the volume on devices such as cell phones and headsets. This question here says, you've been hired to invent a whistle to call a trained pet dog back to its owner. The whistle must be heard by the dog, but not by humans. Predict the range of frequencies you could use for the whistle. So, based on the chart we have, if we have it sort of lists a dog's hearing and a human's hearing on this chart. And if we have a whistle that is higher than 20,000 but lower than 50,000, a dog would be able to hear it. A dog could also hear something on the infrasonic side, although there's a smaller range that we could use there, so that might not be as worthwhile. Unlike with humans, the ear is not the only detector of sound in elephants. Elephants also have hearing receptors in their trunks and feet. Elephants have been seen pressing their trunks against the ground while trying to detect sounds. They also lift up one foot and press the other three more firmly against the ground. Elephants do this because they send sounds through the ground as well as through the air. So elephants can detect infrasonic sound waves, and it says that infrasonic sound produced at 15 hertz to 35 hertz and can be as low as 117 decibels. As loud as 117 decibels. Typically, the sound travels much farther than higher frequencies. Some researchers think that the bottom of an elephant's foot actually resonates with these low frequencies like a drum. So you can write this down about infrasonic sound waves. They're characterized by an ability to cover long distances and get around obstacles with little energy loss. There's the comment about elephants. We can use infrasonic sound waves to monitor earthquakes, to chart rock petroleum formations below the earth, to study the mechanics of the heart. Ultrasonic waves, or ultrasound, like any wave, they carry energy that can be absorbed or reflected by the medium which it is traveling. Unlike X-rays, ultrasound is used in medical diagnosis and therapy with no side effects, though. There's such a small amount of energy in ultrasonic waves compared to X-rays that they can't cause any sort of problems to internal organs. So a baby being examined by an ultrasound is shown here. They wouldn't use an X-ray because they don't want to harm the baby in this case. Focused high-energy ultrasound can be used to destroy unwanted tissue as well. the tip of a probe, where the tip of a probe oscillates at 22 kilohertz. Gall and kidney stones that are otherwise too large to pass can be shattered with a short pulse of high energy ultrasound if it's focused on the stone. So you can sort of destroy gall and kidney stones without the need for an invasive surgery using ultrasound. So here's what you can write down for ultrasound. Used in diagnosis, used for treatment. Some cameras use ultrasound. There are devices that use ultrasound to detect location of things, so like sending off an ultrasound signal and then waiting for the signal to return. Does sound need a medium? So in 1654, Otto von Guericke, inventor of the air pump, discovered that the intensity of the sound from a mechanical bell inside a jar decreased steadily as air was removed from the jar. When most of the air was removed, no sound could be heard. Von Guericke also showed that the sound could travel in materials other than air. In another experiment, von Guericke learned that the sound of a ringing bell could be transmitted clearly through water. In his experiment, fish were attracted by the sound of a bell in water. So let's think here. Would sound travel faster in water or in air? You might already know the answer to that. We've already talked about it previously, but here it says sound cannot travel through a vacuum. It requires a material medium. So sound, just like any wave, would travel faster underwater than it would in the air. Sound waves, they are longitudinal waves, so they're made up of compressions and rarefactions. This slide here uses a tuning fork to kind of show you how these rarefactions and compressions are generated. So if we strike a tuning fork, we start to have the oscillation, the vibration of the tines of the tuning fork. On the inside of the tuning fork in B, we see a compression of air or particles in the air, and on the outside we see a rarefaction. And then when the tuning fork kind of bends back to the amplitude in the opposite direction, we have compressions of the air particles near the tuning fork and rarefaction within the two tines of the tuning fork. If this motion is repeated, we can see how sound can travel, where we have these compressions and rarefactions, and the particle motion is longitudinal away from the source of the vibration. These particles of air only vibrate locally, so they kind of move back and forth locally where they were. They do not move from the source to the receiver. We can measure a wavelength and an amplitude, just like we can for transverse waves. The wavelength would be the length from a compression to a compression or a rarefaction to a rarefaction. The amplitude of the sound wave would be how loud it would be. So the higher the amplitude, the louder the sound. But there's a few other things we consider with sound waves that we might not consider with other waves. One of them is pitch. Pitch is the frequency of the sound waves. So as the frequency of a sound wave increases, the pitch increases. The lower the frequency, the lower the pitch. And of course, because sound is a wave, we use the universal wave equation to determine some of these characteristics. So sound waves, they travel as a longitudinal wave. Amplitude is loudness, frequency relates to pitch. Use the universal wave equation to relate pitch, frequency, and wavelength. So pitch would be our frequency, so it would be our F. If we rearrange the V equals F lambda equation to F equals V over lambda, then as our velocity increases, we would have an increase in our pitch. And as our wavelength decreases, because it's being divided, we would have an increase in pitch. This question here says the sound from a trumpet travels at a speed of 350 meters per second in air. If the frequency of a note played is 300 hertz, what is the wavelength of the sound? Using the universal wave equation, we need to rearrange for lambda which would be V over F. So it's simply 350 divided by 300. And we have 1.16 repeated. Rounded to two significant digits, we have 1.2 meters. So you're standing at a straight road and see lightning strike on the ground ahead of you. 3 seconds later, you hear the thunderclap of the lightning. Since the speed of sound in this situation will be 330 meters per second, how far will you have to walk to reach the point where the lightning struck? So if you see the lightning strike and you hear the sound 3 seconds later, that means that you are very close to the source of, or to where the lightning struck. And to find that out, we need to use our V equals d over t equation and rearrange that for d. So d equals v times t. So v is 330 times t, which is 3 seconds. You are 990 meters, or about 1 kilometer away from the source, or from where that lightning struck, if you hear the sound in 3 seconds. The external ear is shaped to collect sounds, which then travel down the auditory canal to the eardrum. The eardrum is forced to vibrate by successive compressions and refractions coming down the ear canal. Attached to the inside of the eardrum are 3 small interlocking bones, which transmit vibrations to the eardrum, or from the eardrum to the inner ear. And these 3 little bones, they are the hammer, the anvil, and the stirrup, although they have other names, but those are the ones that we use colloquially. They then cause a vibration to happen right by the cochlea, which is inside that cochlea we have little hairs, and those hairs end up vibrating. The way those hairs vibrate, they send an electrical signal through the auditory nerve, which then goes to your brain, so your brain can interpret the sound. There are about 23,000 microscopic hairs in the cochlea, in each ear, right? So those hairs, each hair is connected to a cell that, and that information gets sent to the auditory nerve. You can copy this slide down. You don't need to see the picture there, but how this is basically explains that the ear transforms sound into electrical signals, which the brain then interprets. And there is the study of biophysics, where we basically look at the physics of the body, and part of that is electrical biophysics. So how the nervous system transmits messages, not only sounds, but all messages using electrical signals in the body. The cavity inside the middle ear is filled with air and is connected to the mouth by the Etruscan tube. I've always had trouble with that word, which only opens when you swallow or yawn. At these times, the air pressure inside the cavity will equalize with the air pressure outside. If it becomes blocked, pressure equalization will not occur. Cochlear implants are used to help people hear. And they basically are devices that consist of electrodes that are embedded in the cochlea of the inner ear to stimulate the auditory nerve. Cochlear implants provide a crude approximation of normal sound, but cannot yet fully produce the sounds experienced by someone with full hearing. We're now going to talk a little bit about sound safety. As you age, the range of your hearing starts to decrease. And some of the reasons to this are just general the deterioration of the body as you age, but others could be because of exposure to loud noises, because of environmental or industrial noises that a person might experience over a long time. If you hear a particularly loud sound, it could actually cause the some of the hairs inside your the cochlea to actually vibrate too much to the point where they lose their connection to the to the nerve cell that they were using to send signals to the brain. So that could also happen where you lose your hearing. The unit typically used to measure the intensity of sound is the decibel. And note that the unit is the bell, but it's always almost exclusively written in terms of decibels, so we typically just use decibel. It's named after Alexander Graham Bell, and the decibel unit is logarithmic. You have not seen logarithmic units too often, so the idea behind a logarithmic unit is that as it increases by 1, we have an increase of 10 times in terms of intensity. Lots of units that are used for intensity are logarithmic. So here, this question says, for each of the following pairs, state the number of times the sound intensity of the first sound exceeds the second. So if we go from 30 decibels to 40 decibels, we've actually increased the intensity of the sound by 10. If we go from 100 or 70 decibels to 100 decibels, 10 minus 7 is 3. So we've increased the intensity by 1,000 times. Note that when I'm doing those, I kind of drop the 0 because I have to work with the bell unit. So as we increase by a bell, we end up increasing by 10 to the power of that 10's digit number for the decibel. Sound levels greater than 100 decibels that persist for more than a few minutes will harm your hearing. So this slide here gives you some examples of things that could really harm your hearing. But intensity is important to consider when we consider the time as well. So you could hear something that has a sound level of 90 decibels for a short period of time, and it won't harm your ears as much. But if you hear it for a prolonged period of time, then it will. Other sounds that are really high in terms of their intensity, you would feel damage from them just from hearing them for even a very short period of time. So our range of hearing diminishes with age and exposure to loud sounds. This chart gives you a permissible exposure time. So 90 decibels, if you hear that for 2 hours, you won't have too much damage, but hearing that for longer than that, you could start to have damage. When we get to 115 decibels, you're talking about 30 seconds. You could be able to hear that before you start experiencing hearing loss. And the last question to think about: why do some hunters have loss of hearing in only one of their ears? Well, some hunters would kind of aim and shoot on one side of their body, and that means that the ear on that side of their body would be closer to the source of these high decibel sounds, these high intensity sounds. That could cause hearing loss in that ear.